Thank you very much. Thank you again for having me in this amazing workshop. I wish I could be in California, but doing it also virtually is very, very nice. So as you said, I would like to start my talk with this question. Oops. Oh, all right. So do you know what are the type of accident that autonomous vehicles are right now having? And that's basically the question for the crowd. Feel free to unmute. So there is a report saying that 98% of autonomous vehicle accidents are due to something. And I'm curious to see what you think is this something. And these are real accidents. Sorry?
People not paying attention, being on the phones.
So this is an accident of the autonomous vehicle itself.
Oh, autonomous vehicles.
So it's companies that are trying to develop autonomous vehicle, and this leads to an accident. It doesn't necessarily mean that people are dying or there is an injury, but there is an accident. And they have to actually report it, and there is a actually interesting report online that we can check what are the type of accident that right now the technology is facing.
So we have some chat saying people around the vehicle are being distracted by the vehicle, or people stop the autonomous vehicles. So there's some alluding to the fact that it is the interaction between the vehicles which is problematic.
Not bad.
Not bad.
So, but what is the behavior of the autonomous vehicle that actually is leading to an accident? Is it, for instance, the fact that the AEV is not able to detect an object or a car and it crashes into the car? It goes off road? I don't know.
Right. So some failures of perception are definitely have been some previous causes of accidents that something was in front of the vehicle and the perception was not able to detect it.
I see. Good. So it's almost none of them. And I have to confess, I was quite surprised because we all have our intuition. I've been working on autonomous vehicle for 20 years, maybe, or 10 years. And we always are worried about a lot of perception problem, detecting everything and so on. It's true that sometimes this is the reason. But in this report, they said that 98% of autonomous vehicle accidents are due to an unexpected stop of the vehicle. And it was an accident coming from the back. So other human drivers actually crashed into the AV because the AV decided to stop. Why the AV decided to stop? The other drivers could not actually anticipate that. And it's indeed often because of the surrounding of other cars, but also maybe the behavior of other pedestrians or even other bicycles. Mm-hmm. The AV was able to actually detect all these agents, but it was not able to anticipate or adapt to the behavior of these traffic users or agents. So basically, I claim that it's not a perception problem, it's a forecasting one. The autonomous vehicle is not able to predict what traffic participant will do around the car and adapt and plan a path accordingly. So this is not only a problem for self-driving cars. Let me introduce you another type of autonomous vehicle, our robot. It's called Lumo. It's actually a Segway robotic solution robot that in this case is navigating alongside humans, pedestrian, in Lausanne, Switzerland. So as you can see, it actually did a very good job. It was able to avoid people, and it's potentially quite successful in navigation in this context. But once it actually was supposed to navigate in front of this crowded environment. Our robot actually failed. So and failure is basically the robot freezed, was not able to move forward. And in fact, it could have moved forward, but in a reckless manner. So it will have asked humans to move away and to be able to actually get to the destination. So what's the problem here? I claim that AI must understand social etiquette and must learn to anticipate behaviors, must learn to anticipate, for instance, human-human interaction. So if we look at the AI of an autonomous vehicle, and I'm using again our robots as an example, the common practice was to basically first solve a perception task, and then, given the perception task, solve a planning problem, detecting which path to take. And this was actually maybe implicitly driven by one of the definitions of AI, which is any device that perceives the environment and takes action for its goal. So it was quite natural to suppose that we can create two teams, one team focusing on computer vision, doing perception, sensor fusion, and another team doing planning to make sure that basically the robot can do whatever we want. It's true that both of these pillars are very, very, very important and challenging, but again, that's not good enough. For instance, in this example, if we have three paths that are physically possible, so if you compute some cost map over the scene, you detect all these objects, these three paths have potentially the same weight. But one of them is socially not acceptable because it will go between two people talking to each other. And we humans know that the unwritten rules of social interaction tells us let's not actually cross two people talking to each other. Let's take another path. But another one is, in fact, we can see that the path on the left is not also good because we might actually hit that pedestrian that is walking in the right direction. So there is only one path that will be actually social compliant is the red one. So what is missing in these two pillars is another pillar, which I call social forecasting pillar. And by combining our social forecasting pillar with the perceiving and acting pillar, we can actually develop socially aware AI, AI augmented with social intelligence. So social intelligence is this capacity to effectively navigate and negotiate social interaction. For us, social intelligence is the capacity or the ability to predict this interaction and be able to basically make a decision based on our understanding of what humans will do. So this is really the goal of our lab, which is how can we better predict the future, predict the interaction between humans, between agents. And for me, when I talk about human, it's other drivers, other bicycles, other animals, or other pedestrians, any moving agent. And how, even if we think of improving our forecasting, how it can actually help perception and acting. One naive way is actually to see this as a sequential pipeline. I first do perception, and then I forecast. Thanks to my perception and thanks to my forecasting, I do planning. But we believe that, no, there is an interplay. They can actually help each other. And if we look at them jointly, we might have a much more robust solution. I'm going to talk about this at the end of the talk. So let me share a bit with you now what we have been doing for each of these pillars. And I want to start with our social forecasting pillar. We can formulate the problem as follows. Given a sequence of states, for instance, the coordinate of an agent, in this example of a vehicle, predict the future state, the next 5 seconds. And the challenges are that we need to actually model interaction. I use the word social because it's like multiple dynamic agents, multiple vehicle. For me, a vehicle is a social agent. It's interacting with other vehicle, other being. And we also need to handle the uncertainty. So there is a multimodal distribution in the output. And can we actually robustly predict this multimodal behavior? So this is one example in the self-driving car context, but this is also true with respect to humans. If we want to develop a robot that will interact with humans, we exactly want to do the same. So I'm going to focus on humans and pedestrian because it's much easier to run experiments and potentially I want to also show or I claim that if we are able to have a robot that will navigate in crowded human environment, we will have the AI to actually operate any autonomous vehicle because the navigation of a robot in crowded human pedestrian-only area has much more non-linearity. Humans have much more non-linearity than vehicles. And the environment is not as structured as the road. So it's even a harder problem to solve than a self-driving car context. So I want to show that if we have the tools, the methodology to solve that in human environment, then we will have the same technology to solve it in any other environment. So for many years, the common practice was to use what I call knowledge-driven methods. For instance, social force modeling, or which you're supposed to design some attractive functions and repulsive functions coming from our intuition of how we actually navigate or interact in crowded environments. And there were also other nice work using discrete choice modeling. You need to define a utility specification, and you can use the RAM theory, the random utility maximization theory, to solve this decision-making process. This is great. So they have actually amazing interpretability. We really understand the model, but they have limited prediction accuracy. They fail to model long-term dependency and complex interactions. So very naturally, in the deep learning era, we decided to rethink of this problem with data-driven method. So the first thing that you need is data. So what we did, we installed actually cameras and sensors in the world in where we think has the highest interaction, and train station have amazing crowded interaction. So we put cameras in train station. This is one example of a corridor in Lausanne train station from top view, where we put, for instance, 32 cameras. And we solved the computer vision problem of detecting and tracking humans across all this network of camera. So these are the type of signal that we were capturing. We were also using thermal imaging. And from all these sensors, we were able to basically detect and track humans in this environment. Every dot is a commuter in this corridor. So we collected a lot of data. In fact, we were able to run this for several months and years. So we are able to extract statistics like heat map, the density of humans, where they're coming from, where they're going. And this had a huge value for the train station. But for us, it was an amazing opportunity to actually see if we can develop the AI that will match the human behavior, that will be able to actually predict or navigate as good as human in crowded scene. So this is the amount of data that we have collected. And back then, when we did that, it was in 2014. The red dot is the amount of data that was available. And that's why nobody could really do actually deep learning technique back then, because there was not enough data to solve this problem with deep learning. And now we have enough data, so we can rethink this problem with deep learning. And we recently actually created a new challenge based on all the data that we found. It's called TrashNet ++ challenge. You might know where the inspiration of the name came from. So this is a challenge where we are actually sharing all the training example of all these trajectories, and you have all the tools to basically train your model, submit to our challenge, and get the quantitative numbers, and you can actually have a leaderboard and so on. The one issue in this field of trajectory forecasting is that they were not a unified benchmark. So people were potentially using the same data set, but they were not using the same samples within the data set. They were not actually separating the training and testing the same way. And in fact, one of the exciting difference of trajectory forecasting with other tasks is statistically, if you don't do a good sampling of your trajectory, you will do, a lot of the examples are linear behavior. So you could have an amazing performance because only 1% of the time people have nonlinear behavior. So your linear model will be amazing. But if you rethink your sampling strategy and you only focus on nonlinear behavior, then all your numbers can actually become very bad. So you want to make sure that everybody is actually focusing on nonlinear behavior to do an evaluation. This is what we're doing here. So what we can do with all of this data, we can now play with it and try a lot of data-driven methods. So we started with LSTM. It was, I believe, to the best of my knowledge, the first data-driven method to solve trajectory forecasting, our social LSTM work in 2016. And the main contribution of that work was to how can we actually model multiple sequences jointly. So basically, I need to predict the behavior of human. Each person can be seen as a sequence, but then I need to do this jointly. So everybody is a sequence. How can I actually model interaction of multiple sequence and do multiple sequence prediction? And we proposed a simple way to do this. We actually suggested to have another pooling strategy based on an occupancy map and a tensor to actually fuse the hidden state of multiple sequences. And this is the formulation. You can look into the paper for more detail. Another issue that we realized back then is that naively, we only trained our model with the L2 loss. We wanted to minimize the average displacement error of our forecasting task. And we might actually get good average behaviors, but we were not modeling the multimodality nature of the task. So we then look at other type of loss to make sure that we can model the multimodality. So for instance, one of them is the winner takes all loss, as you can see, that will allow our network to actually output a distribution. You might see where I'm going. I'm talking about a distribution, generating a distribution. And it was, again, a very natural thing to do to study how well a GAN and generative adversarial network will do the job. Are they able to basically learn the distribution of all these trajectories? I heard some word. Is there any question? Feel free to interrupt me if there is any question. So we then look at the problem with an adversarial loss. We were wondering if using an adversarial loss will allow us to better model the multimodality nature of our data. As you might know, one of the biggest weaknesses of GAN is mode collapse. So we were able to actually have better modes in our output distribution, but we were losing some of them. So we were suffering from mode collapse. In other words, the quality of our output trajectory was quite nice when it was matching the right mode, but sometimes we're actually missing possible output, which could be quite critical. So what we looked, we actually dig into a generative adversarial network, and we wanted to see if we can improve this issue of mode collapse with GAN, and even the issue of sample quality. So when we look at GAN, so the brief overview of GAN, so you try to train a generator based on a discriminator during training. So you jointly try to train both your generator and discriminator. And once you are happy in this min-max game, you only keep the generator and you generate your output, in our case, trajectories. But at test time, you're not using the discriminator anymore. You actually can throw it. And we thought that this might not be very smart. Why are we not still using our discriminator at test time? So what we did, we started to look if people were actually suggesting to use the discriminator at test time, and it was the case. So there were a few new strategies in 2019 that were suggesting to use your discriminator at test time and use it basically to, for instance, reject sample. If the discriminator is classifying them as not possible, just generate again. And potentially you might be able to improve the quality of your generator. Or use other type of sampling strategy, Monte-Carlo techniques. What we decided to do is to still use the discriminator at the test time, but not as a rejection strategy, but as a refinement strategy. So we generate something, but we still use the discriminator to refine our trajectory. And update, basically provide the update to the generator and generate until the condition is met by our discriminator to basically be full. And by doing that, we realized that we can actually outperform existing work in modeling multimodality. So we are less affected by mode collapse. So we can actually better predict all the modes. And we tried for trajectory, but also with other toy examples, such as, one very popular example of trying to construct 8 quotient, for instance. So you have a set of points that are following this distribution, this 8 distribution, and can I actually make sure that I'm not losing any mode? And we were showing that our collaborative sampling strategy was able to do state of the art or beat previous work using other strategies. We also test this idea for other generative problems, like generating signal of higher dimensionality, like images. And we were showing that basically we all know that it's very difficult to train GAN, and the reason is that we don't have infinite capacity. So we have limited capacity, limited training power. So it's very ambitious to suppose that our generator can be trained in an optimal way. But the discriminator maybe is quite powerful. So we might be able to get one extra more mile at test time if we still use it to improve the generation. And this is what you see. So the improvement is not drastically, it's just one extra mile to still improve the quality of the sample based on your fixed generator. So this is basically the recap. As you can see, we really thought about how to rethink all the loss function and the supervision of our forecasting task. So we are also obviously applying this to not only human-human interaction, but as I mentioned, also with respect to a self-driving car context. And this is just a visualization for you to be aware that these ideas can also be applied to, for instance, predicting car dynamics at roundabout. So roundabout is a very exciting opportunity for self-driving cars because it's a lot of reading the behaviors of other cars in the roundabout. So there is a lot of interaction. You can either accelerate to enter a roundabout or actually slow down, and it's quite exciting to see if AI can learn this interaction and do as good as humans. So this is what I wanted to say about forecasting. I think I have 12 more minutes, and I'm gonna share with you what basically we have been doing for the other pillars, the perception and acting pillars. So for perception, this is quite a crowded area. Many people are working on it, and for many years, detecting was already a huge challenge. But in our case, because we want to better predict the future, we also are challenging what we should perceive. So if I perceive bounding box or just the coordinate of humans, is it good enough for me to predict what they will do? And this is basically the motivation for us to go beyond detecting just bounding box or doing segmentation of the scene at the pixel, but we want to extract more semantics. So for instance, understanding body pose will or might change maybe our forecasting accuracy. So if we are modeling the body pose, we might be doing a better job to predict what these humans will do in the future 5 seconds. So we have actually new algorithms that are, I believe right now, state of the art to do a pose estimation. It was quite also challenging because with open pose and Google and Facebook trying to work on this, the competition was quite hard. But we have a live demo. You can actually click here, a Vita demo. I don't know actually if I click what will happen. Do you see the camera? Do you see it? So this is a live demo that you can all do. Click. It's also on our website page, and it will just run your camera and do real-time pose. It also works with an iPhone. And the main contribution of this work is basically using fields and a slightly elegant way to use field so that it's robust to low resolution images. So to, for instance, very small humans. So we are able to extract the pose of very, very small humans because we have a way to model the images with composite field, which seems to be quite robust to these challenges. So let's see if I stop this tech. And we are naturally also interested to extract as much semantic as possible, and again for the same goal, to better predict the future. So activities can be another example. And why we do that? Because we are into this application of autonomous driving or navigation. We want to also think about how to be efficient, and one natural way to be computational efficient is to think of this problem as a multitask learning problem. So to share a common representation to solve multiple perception tasks. And this is also what we are currently doing, and we're quite excited, is, for instance, can I perceive 32 attributes on humans in a single feed-forward network without having multiple networks that will do each of these tasks independently? And can I just have one backbone and 32 outputs and do as good as having an independent network for each task? We are actually we have quite exciting result. We will put a paper on archive by the end of this week, I think, showing that we can potentially match the performance of independent network for each task with just a single multitask learning framework by just rethinking how we actually deal with the gradient. And we will feel free to send me an email if you're interested on this line of work. This is some of our illustration of the pose estimation. Here we are also doing tracking, pose tracking. And it's quite exciting because this algorithm, I'm always impressed by how our community and was able to get this perception problem working now. So this is quite amazing. We are also doing this to extract 3D. So this is quite also common. Another thing that is a bit less common, but still a lot of labs are already doing it now, like for instance, TRI, Adrien, and also at Stanford, is can I actually predict the intention of humans, the fact that they would actually cross the street or not. And this is also as part of my multitask learning. So I want to potentially detect attributes on my pedestrian, and one of these attributes is, will it cross the street or not? And this is something that we're also quite excited to solve. So let me skip this. I can skip also this in interest of time. I want to now only talk on the acting and planning pillar, what we have been doing. So for acting and actually planning, one of the very nice line of work is basically using reinforcement learning to learn what are the nice set of action that a robot needs to do to navigate a crowded scene. And there have been a lot of contribution in the community of how to rethink the reinforcement learning framework and so on. And what we really wanted to study, we wanted to show that if you rethink the latent representation, you will be able to do a better job in solving the navigation task in a reinforcement learning framework. So previous work, they model the environment, the state of the environment by focusing only on human and robot interaction. So where are other humans with respect to the robot? And what's the state of the robot? And this was the input to learn a representation to solve the reinforcement learning task. What we added to this is that we should also learn a latent representation of how humans in the crowd are interacting. And we showed that if we also try to model human-human interaction, in addition to human-robot interaction, then we do a better job in learning a policy to have a robot that will navigate a crowded environment. And this was our crowd-robot interaction paper at École. So it's almost the end of my talk. I have a few minutes. So I want to also basically share where we want to go. We don't have any evidence that this is true, but my vision, which I like to also share with Stefano, is that everything is about learning a good representation. And many of the current success story, at least for autonomous driving task for perception and planning, is if you do a good job in learning a latent representation, you potentially have done a lot. You're already there to solve your problem. And then, if that's true, how can we even make sure that this representation that we learn is robust to adversarial example or out of distribution? So what I'm interested in is to also think representation learning across pillars. So for instance, I have this architecture Can I learn a shared representation that will jointly do prediction, my social forecasting task, and my planning task? So one, for instance, I can train it in a supervised way with offline data set. And the other one, maybe with reinforcement learning supervision. And can I even push this actually even more by doing also perception? So can I have a latent representation that will do perception, forecasting, and acting jointly? And I refer to this maybe as a universal representation. And I'm curious to see if this is possible and if we can show that by doing that, it brings a bit more robustness into our system.
So we have a, sorry to interrupt, we have a quick question. So let me just read it. This is on chat. So the question is by Brett Jefferson, and he's asking, would predicting if a pedestrian will cross a perpendicular street, thus interfering with a right-hand turn, for example, be easily adapted to your forecasting framework? How would you distinguish walking on a sidewalk from walking across and obstructing an intended path?
I'm not so sure if I understood correctly the question. Can you maybe, did you understand?
Brett, do you want to unmute yourself?
And I can unmute.
Oh, well, then just go ahead and ask.
Thanks.
Yeah, so, you know, you kind of had you know, you showed us that basically if the pedestrian is going to walk in front of the vehicle, you know, you got some color coding associated with the model that said, oh, they'll turn blue if they're going to, you know, cross, you know, the vehicle. But if I'm going down the street and I'm going to make a right-hand turn, but someone is like that, oh man, if you go back just a little, you can see them like walking across where I would make a right-hand turn, for instance. Would your model kind of be easily adapted to predict those kind of obstructions?
So maybe let me say this. I don't know if it will answer. Our goal is to do as good as human. So we don't have any ambition to do better than what we humans are doing to predict what we see. Mm-hmm. So it turns out that when in Europe, we have all these zebra crossing and there's no red light. Me as a driver, I see the environment, I need to take a decision to actually brake because there might be someone that will cross. Sometimes I might be wrong, or sometimes I might be correct. And we want to make sure that we can match human behavior and not be too conservative or too actually critical. So I don't know if I'm answering your question, but our goal is not to actually solve this task perfectly, but to solve it potentially in a way as good as what we human will do if we look at the scene.
But so it would seem to me that it's an easy thing for humans to say, oh, I just won't turn right until this human is out of the way. You know, that would seem kind of like an easy human task, but is your model kind of prepared to deal with right-hand turns, for instance?
Yes, I mean, absolutely. But you will be surprised right now. In a lot of the autonomous vehicles are being too conservative. So and it's quite dangerous. If there are pedestrians just walking on the sidewalk, they might think that they need to stop, and that's not what we want. We want the car to stop really when there is a possibility to cross, or the same situation where a human will decide to stop. And if we have the data for it, we have collected human drivers, and if we know when they want to stop because of the context, we want the AI to learn to do the same.
Okay, great, thank you.
Are you using the pose to learn this, or is it just from detection and predictions?
Yes, we're using the pose. So in this video, we we were testing two things, either using the pose or the image, the whole image.
Mm-hmm.
And when you use the pose, it also helps a lot.
Okay.
Yes. Should I continue? I'm almost done.
Just go ahead and wrap up maybe, and then we can have more questions.
Yes. Actually, I can wrap up. So basically, something that we are also we should all check is about the robustness of the system. And we are currently also studying if there are any realistic or feasible adversarial example to our system that will fool our algorithms. But they are configuration of the environment that are actually possible. So this is something that we're quite excited also to work on. And then, so let me then go right away to the conclusion. So I've talked about these three pillars. This is on the left, Switzerland now. I hope that maybe Switzerland will look like on the right. Everything that I've presented, we have open science policy. Everything is online. Every paper is published if there is a code online. So this is the policy of the lab. So feel free to, if you're interested in any of our work, the code is available. And we are also teaching actually this class, deep learning on autonomous vehicle, with our little robots. And the students have actually a real world challenge of competing against each other, whoever comes the first on a race. It was very exciting. Voilà, thank you.